Hello everyone, my name is Rucha Srikanth Khalate. I am pursuing computer engineering from Vidya Pratishthan's Kamalin Bajaj Institute of Engineering and Technology, Baramati. Today I am going to present a seminar on topic DiffNet, a learning to compare deep network for product recognition. Let us start with the introduction. Nowadays, we know that artificial intelligence is used in many areas. We can do the payments with the smartphone. Due to this, unmanned AI retail is becoming increasingly popular, such as Amazon Go, Bingo Box, Toe Cafe. These are the examples of unmanned AI retails. RFID technology for product recognition is a good solution for smart containers. This RFID technology is good solution, but it adds up the cost, which ultimately cuts down the profit. The gravity sensors the gravity sensors are used to detect the product being moved. For object detection, some containers use the gravity sensors, but which are not accurate enough and has the great limitations. A deep learning algorithm have been adopted in many visual analysis problems. A deep learning algorithms like object detection algorithm, classification algorithm, and tracking, segmentation. In this topic, we are going to focus on object detection algorithm. We propose a new object detection method by comparing two images captured before and after the purchase. Now we will see the problem statement. This is the problem statement. In unmanned retail shop, system detects the different object in a pair of images photographed from almost the same angle in the same environment from unmanned container before and after the purchase. Now we will see the literature survey. Convolutional neural network is deep learning technique which demonstrate a great capacity in a variety of fine-grained image recognition tasks. Second, LO 9000, better, faster, stronger. It's one-stage approach which treats the detection task as a regression problem and directly predict the bounding box coordinates and categories of the target object. Now we will see the algorithm, method, and technology. In this section, we are going to see the details of proposed DiffNet for detecting the difference between the pair of images. This DiffNet architecture we have constructed in a simultaneous. It consists of two feature extractor, a feature fusion operator, and a regression network. Let us see the architecture of DiffNet. So this is the architecture of the DiffNet. These are the input images. These are the feature extractors. This is the feature fusion operator. This is the regression network. This is NMS, and these are the results of our DiffNet method. So these two feature extractors takes these images as an input. As these two feature extractors shares the same parameter, these images are mapped into a same embedding space where the input is compiled. This feature fusion operator takes the information which is generated by this feature extractor and pass this information to subsequent regression network. This regression network, after obtaining the feature fusion, we feed it into the regression network for regressing bounding boxes of different objects to predict the categories. For this, we are following popular yellow V2 detector method to design the loss function. Now, we will see what is this NMS. This NMS stands for non-maximum suppression. NMS is used to set the most appropriate bounding box for an object. There may be a chance a single object can have multiple detection by our algorithm. Due to this, single object have many bounding boxes. To overcome this ambiguity, non-maximum suppression is used. The NMS selects the bounding box with the highest value and takes the IOU with the other bounding boxes. If the IOU value is greater than 0.5, then we select that bounding box and we eliminate the other bounding boxes. Then our result is generated. These are the results of our DiffNet method. Now we will see. Sorry. This is the information about the feature extractor, feature fusion operator, regression network, which we have seen in the last slide. Now we will see the training. The proposed DiffNet is fully convolutional and it can be trained end to end. DiffNet is like one-stage detector. The training involves label parsing, default anchor box setting, loss function, and data augmentation. Let us start with the label parsing. We divide our image into S by S grid cells. So let us consider this as image, and we have divided this image into S by S grid cells. So these are the grid cells. So each cell has a ground truth in the following form: P of obj, P of A, P of B, X, Y, W, and H. Now let us see what is this P of obj. This P of obj denotes the probability that there is an object falling in the current cell or not. This P of A denotes the probability that center point of the target object fall in the image A. Similarly, this P of B denotes the probability that the center point of the target object fall in the image A. Similarly, a P of B now this x and y are the center coordinates of the bounding box. This w is the width and h is the height of the bounding box. Now see the default anchor box setting. We apply the anchor box in a DiffNet. It reduces the ambiguity of the learning problem and helps to train a better detector to predict the offsets and confidence instead of coordinates. The anchor boxes are used whenever we have one cell and two objects. In order to handle this, we are going to input the predefined set of shapes called the anchor boxes. So these are the anchor boxes and these are the grid cells. Data augmentation. The data augmentation is useful to train more generalizable deep networks. To make our model more robust, we randomly adjust the hue, brightness, and saturation of our input image. This is called sampling. After this, each sample patch is horizontally flipped with the probability of 0.5 and it is resized to 512 by 512 to fit the input size of our model. Now we will see the loss function. The loss function is the function which quantifies the error between the output of the algorithm and given target value. The loss function for the DiffNet is based on LOV2, which is composed of prior loss and regression loss. The prior loss helped the DiffNet to learn the shapes of the prior boxes more quickly. This is the equation to find the prior loss. Now we'll see the regression loss. The regression loss consists of objectness part, coordinate part, and the classification part. The aim of regression loss is to classify the image in the box, in which box it is belong to. These are the equation for the regression loss, and this is the equation of loss function. During the training, we optimize the following multi-object loss function. So this is the equation. Now after training, we will see how our algorithm is working actually. These are the some results of our DiffNet method. We will see this one by one. In this figure, there are two images. In this figure, there are two images. One is captured before the purchase and other is captured after the purchase. Let us consider this as image A and this as image B. In image A, there are 5 water bottles, and in image B, there are 4 water bottles, which means one water bottle is missing in the image B. So, aim of our DiffNet is to calculate this difference. So in image B, here we can see there are two rectangles. One is of color green and other is of color red. So this green color rectangle represent the ground truth, and the red color rectangle is the output of our DiffNet. As here we can see these two rectangles are very close to each other, which means our algorithm is working perfectly. In image B also, the red color rectangle is very close to the green color rectangle. In image C also, here we can see this green rectangle is very close to red. And similarly in image D also, we can see our ground truth is our out, output is very close to the ground truth, which means our algorithm is working perfectly. Now we will see the comparison of our DiffNet with the other technologies. The structural similarity index algorithm is used to calculate the similarity of pair of images, but this algorithm is not robust to light changes, pixel offsets, etc. The method only achieves 2.85% of MAP in our test set, which is much slower than our deep learning based method. So in this uh, table, we can see the MAP of SSIM is 2.85, which is very less than our MAP of our DiffNet, which is 95.56%. And the inference time of SSIM method is very large as compared to our inference time of our DiffNet method. From this, we can say that our DiffNet is working better than this SSIM method. Now, second technology, RFID technology for product recognition is good solution for smart container, but it adds up the cost and reduce the profit. However, our definite technique is good for product recognition, and it is cheap as compared to the another technique. Now the third, a smart containers are used. A smart container use the gravity sensors to detect the product being moved, but it is not accurate enough and has a great limitations in the maintenance. As compared to this method, our definite method is more accurate and has less limitations. From all this, we can say that our definite method is working better than other methods. Now the conclusion. In this paper, we propose a method to detect the different object in a pair of images. By using this technique method and based on the experimental result, we are able to detect the different object very easily, and we can use it in the unmanned retail shop for object detection. Uh, we propose our pairwise image difference detection algorithm called DiffNet. In this method, we combine the characteristics of learning similarity measures of Siamese network with the one-stage detection method. A promising future direction is application in the unmanned commodity container to detect the location of different goods before and after the purchase. And this technique achieves the good positioning accuracy with the fast inference time. These are the references. Thank you.